All right, so we're now on to the last section of chapter 11. And here we're going to start with vapor pressure and work our way into talking about phase diagrams. But we have to get the vapor pressure concept down first. So vapor pressure is simply the pressure when you have a liquid and that liquid has it's volatile, has some vapor pressure. That vapor pressure is going to be the amount of gas, the partial pressure of that gas above that liquid. Now, we can measure vapor pressure in a couple of different ways, and I'm going to show you, this is sort of a thought experiment here. So here we've got some liquid ethanol, and down here we've got a flask that is completely evacuated, so there's no pressure whatsoever in that flask. If we add ethanol to that flask, we will find that some of the molecules are going to start evaporating from the liquid phase going into the gas phase. And so as that happens, the partial pressure of the ethanol in the gas phase is going to increase. Well, some of those molecules that are in the gas phase are also going to return to the liquid phase. Not much we can do about it because some of the molecules go from liquid to gas and some of the molecules go from gas to liquid. Well, the point at which we get the same number of molecules going from liquid to gas phase as we have molecules going from gas to liquid phase, that is when we are at equilibrium. So the system will come to equilibrium. So we'll have the same number of molecules going each direction. At that point, the vapor pressure or the partial pressure of that gas should be constant, and we call that the vapor pressure. So turns out you can do this experiment without having an evacuated flask. You can do this with just gas in it, but you do have to measure how the pressure changes going from here over to here. So with your best guess, think about this. Maybe you can stop the video here for a second. I want you to think about, how does the vapor pressure change as the temperature changes? All right, so pause the video for a second and think about that. All right, well, if you came up with the concept that maybe the vapor pressure would increase, that would be correct. So the vapor pressure would increase as we increase the temperature. But let's think about why. So first, we're going to go over here to this next page, and over here on the right, I've got a diagram or picture, a drawing here with some molecules in the liquid phase, and then obviously it's open up to the atmosphere, so some of those molecules could potentially escape. But you'll notice that we've got essentially two different kinds of molecules. We've got molecules that are down here in the bulk of the liquid phase that are being pulled on in all directions randomly by all the molecules around it. All of these black lines represent intermolecular forces. Whereas the molecules at the surface, this is our other type of molecule, they are being pulled on by all the molecules around it, but the interaction between that molecule and the air above it is going to be very low because there's just not many molecules in the air. So it's essentially only being pulled down. So as soon as this one gets up to the surface, it's going to be pulled down into the bulk of the liquid and replaced by another one. So those molecules are going to be constantly moving around, going up to the surface and some coming back down. Well, occasionally, some of the molecules will be going fast enough to escape that liquid and get into the gas phase. That's called evaporation. So when the molecules escape, they can go into the gas phase. Now, turns out it's going to be the fastest molecules that can do that. Slow molecules aren't going to be able to have enough energy to get out of there, so only the fastest molecules will do that. As a consequence, we'll find that the temperature of this liquid will decrease. We call that evaporative cooling, which is kind of a cool concept. So the amount of energy that's required to escape is this energy here, the minimum kinetic energy needed to escape. It's this dotted line on this graph. So let's come over here to this graph. This is called a Boltzmann distribution. On the x-axis, we have the energy of the molecules, and on the y-axis, we have the fraction of molecules with those energies. And you'll see that there is a broad distribution of energies for the molecules in a sample. So here we've got a liquid sample at a low temperature, and there's a very broad distribution. Some of the molecules are going very slow. A lot of the molecules are kind of going in this medium range. Some molecules are going faster, and some are going even faster. Only a small fraction of them have enough energy that they potentially could escape if they reach the surface. Now, just because the molecules are here, just because it has enough energy doesn't necessarily mean that it will escape and go into the gas phase. It just potentially could. So you have to keep that in mind. The molecule has to get to the surface. It has to be going the right direction in order to escape. Lots of variables that go into that. All right, as we increase the temperature of our sample, we will find that the distribution of energies will broaden and flatten out. So you'll see it's a little bit flatter here, but we have more molecules that are capable of escaping. We will find that the vapor pressure is directly proportional to the shaded area under that curve. So as the temperature increases, that shaded area increases, and we will find that the vapor pressure will increase. So that's why vapor pressure increases as a function of temperature. As you increase temperature, vapor pressure increases. Now, we can look at this on a graph, and so or a table. I'm going to pull up the vapor pressure of water at different temperatures. So this is from Appendix B of the textbook, and you'll see that we've got 0 up to 110 degrees Celsius, and I've listed the vapor pressures here, so it's a pretty broad range. And so you'll definitely see that the vapor pressure increases as we increase the temperature. All right, if we take that and plot it, on the x-axis we put the temperature, and on the y-axis we put the vapor pressure. Here's water. So you'll see it started off very low, vapor pressure gradually increased, and eventually it got higher and higher and higher. So vapor pressure increases as we increase temperature. We know that already. We will find that this vapor pressure curve will look different for every substance. Pretty much every substance is going to have its own unique curve. All right, and then this is kind of an interesting point, is that the normal boiling point is going to be the temperature at which vapor pressure is equal to atmospheric pressure. Since atmospheric pressure is considered to be 1 atmosphere, and 1 atmosphere is 760 torr, then vapor pressure, when the vapor pressure equals 760 torr, that should be the normal boiling point. And then that boiling point happens to be 100 degrees Celsius for water. Now, I'm going to come back over here, and you'll see 100 degrees Celsius, 760 torr is our vapor pressure. All right. If we've got other substances, for example, ethanol has a much higher vapor pressure at different temperatures. So it has a much higher vapor pressure, and it crosses over that 760 line at about 78 degrees Celsius. So the boiling point of ethanol is 78 degrees Celsius. Here we've got diethyl ether. Diethyl ether is a solvent that we like to use in organic chemistry quite a bit. But it has an extremely high vapor pressure. Even at 0 degrees Celsius, the vapor pressure is almost 200 torr. That means it evaporates really, really quickly. We say that substances that have a vapor pressure are volatile, and so diethyl ether is very volatile. And on top of that, it's also very flammable, so that makes diethyl ether quite dangerous to work with. So you really have to know what you're doing and have to have a fume hood in order to work with it. And then down here we've got ethylene glycol. That is the heat transfer fluid that is used in your car as coolant. It transfers heat from the engine out to your radiator, so it's radiator fluid. And you'll notice it has a pretty low vapor pressure. So even at 100 degrees Celsius, you'll see the vapor pressure, it's only about 50 torr. That makes it possible that you can get the ethylene glycol up to 100 degrees Celsius without it just boiling away. And that's quite useful. All right, so that is the vapor pressure. So now what we want to do is we want to look at phase diagrams. And so here I've got a generic phase diagram. And I want you to be able to reproduce this graph. So our next problem is number 11.2 on the in-class assignment. And you'll see really all it is labeling all of these points. So on the x-axis, you'll label the temperature, and on the y-axis, you'll label the pressure. All right, these lines represent phase changes. So here we've got solid and liquid, and this line represents a phase change from either solid to liquid or liquid to solid. This red line is converting from the liquid to the gas phase. In other words, that line is the same as the vapor pressure curve that we saw over here. It's actually exactly the same curve. So if we were looking at water, it would be exactly that curve that's right there. So that is our vapor pressure curve from the previous thing. So we can convert from the liquid phase to the gas phase. Of course, when we do that, that's called vaporization. Go for gas phase to liquid is condensation. And then you'll notice that we've got solid, liquid, and gas, and they all meet here at this one point that we call the triple point. And the triple point is an interesting point. It's unique for each substance, but it's an interesting point at which solid, liquid, and gas can all be in equilibrium with each other at the same temperature pressure combination. Now, it's a little bit tricky to get a substance exactly to the triple point, but it is certainly possible. And I've got a quick little video to show you what it looks like when something is at the triple point. So I'm going to show you this video for, this one is cyclohexane. And cyclohexane, you'll see right now, it's a liquid. I'm going to go ahead and play the video.
Can you see past that line?
All right, and they've got a little bit of a vacuum here. And you'll notice it's going to freeze up here. There is some vapor. There's some vapor that's up here above that. Oh, see, it froze. So at that point, you had solid, liquid, and gas all in equilibrium with each other at the same time. And then watch, it's all going to melt here in a second. Pretty cool little experiment to do, and fairly easy to do. So not something you can do at home though, because cyclohexane is fairly flammable. All right, so that's what the triple point looks like. I'm gonna turn off that video, and we're gonna go back over here. All right, so that's with the triple point. Now I'm going to show you a video of the critical point here in just a few minutes. But if we've got, if we go up along this, we will get closer to that critical point. I'll explain that here in a moment. All along this curve, usually the slope for this is it's almost straight up and down. For most substances, it does have a slight positive slope, or a very large positive slope, but it does have a positive slope. For water, it ends up being a negative slope. I'll talk about that here in just a moment. But that is our melting freezing line. And then now let's talk about this. So there's a big difference in density between the liquid phase and the gas phase. So down here, there's a big difference. It's about 1,000 to 1. For water, it's about 1,000 to 1. As you increase the temperature and increase the pressure, well, as you increase the temperature of a liquid, its density will go down. As you increase the pressure on a gas, its density will go up. So as we go along this curve, the density of the liquid and the density of the gas get closer and closer to each other. And as they get closer and closer to each other, it's harder to distinguish between the liquid phase and the gas phase. And so the meniscus, that line between the liquid and gas phase, starts to get a little bit blurry. And the point at which the density of the liquid equals the density of the gas is the critical point. And at that point, you cannot distinguish between the liquid phase and the gas phase, and they become one phase. Well, any temperature pressure combination greater than this, we're going to call a supercritical fluid. So if we take a little box here, any temperature that's higher than this plus pressure that's higher than that pressure is going to be considered a supercritical fluid. So that will be considered a supercritical fluid. All right, now that critical point is going to be different for different substances. We're going to look at water here on the next. Oh, and by the way, this is what this looks like when I filled this out. So triple point, critical point, solid, liquid, gas. And then you'll need to know each of these terms: melting, freezing, vaporization, condensation, sublimation, deposition, and then triple point, critical point. And in case you're curious, the supercritical is in that region up there. All right. So that's 11.2, and you guys can do that on your own time. Now here I've got a phase diagram for water, and you'll notice right away this one looks much different than the previous phase diagram, and the biggest reason for that is that it is plotted on a semi-log plot. So the x-axis is normal, it's just got normal temperature. But here on the y-axis, we've got pressure, but you'll see each tick here is one order of magnitude. So this is 1 atmosphere, 10, 100, 1,000. And the reason is it's hard to fit all this data onto one curve and still have meaningful data. But because of that, because of the way it's plotted, the curve looks different. So this, instead of curving this way, actually curves this way. But if we plotted it on a normal graph, it would have looked like the other one that we were just looking at. So down here, you'll see the triple point of water, 0.00098 degrees Celsius at 0.00603 atmospheres. And again, that's where it could exist. The solid, liquid, and gas can all exist at the same temperature pressure combination. All right, you'll notice that critical point is at a really high temperature and a really high pressure. That makes it very difficult to get to the critical point for water with normal equipment. That temperature is really, really high, and so some weird stuff starts to happen at such high temperatures. And 218 atmospheres, you need some pretty serious equipment to hold that in. As a consequence, it's very difficult to work with supercritical water, just because these are very, very corrosive conditions. But one thing I want to point out about this, and you might want to make a point about this, is that water has a slightly negative slope, or it's actually a very negative slope, but you'll notice that it tilts the other way. Whereas on the previous graph, we had a positive slope. Well, here there is a negative slope. What that means is that if you have solid that's right at the freezing point, so if you have some solid that's right at the freezing point and you apply pressure to it, you can melt the solid. The reason for this is the same reason, it's related to the fact that water, ice, has a lower density than liquid. Most substances, that's not true, but for water, that is true. And that's why we have this negative slope instead of a positive slope. So again, if you have something right at the freezing point, if you apply pressure to it, you can cause that ice to melt. And that's definitely what happens there. All right, so that's for water. And then finally, I want to show you carbon dioxide. Again, this one looks a little weird. We do get the slope, but you'll notice it kind of curves away off over here. What's most interesting about carbon dioxide is that at atmospheric pressure, 1 atmosphere, we don't observe a liquid phase. And so most people have never seen liquid carbon dioxide. Well, I'm going to show you a video of it here in just a few minutes. But that's at 1 atmosphere. We've got 1 atmosphere. We don't have a liquid phase. If you have solid carbon dioxide, in other words, dry ice, it will get converted into the gas phase directly. So it'll get converted directly into the gas phase without going through the liquid phase. In order to observe that liquid phase, you need to have it under pressure. The triple point, negative 56.4 degrees Celsius and 5.11 atmospheres. So in order to observe this liquid phase, we need to get that pressure up well over 5 atmospheres in order to get into this range. It is possible to do that. 5 atmospheres is fairly easy to get with not too crazy expensive equipment. So you can observe the liquid phase of carbon dioxide. Now, as we go up that curve, so as we increase the temperature and go up that curve, we'll decrease the density of the liquid, increase the density of the gas. They'll get closer and closer. And again, the point at which the density of the liquid equals the density of the gas, that's the critical point. And you'll see 31 degrees Celsius. That's like a warm day, right? That's not too hard to get to. And 73 atmospheres, while that is a pretty high pressure, that's definitely something that is quite achievable. All right, so that is supercritical carbon dioxide. So now I'm going to show you a quick video of supercritical carbon dioxide. So I don't remember who this is from, but this is from some professor at some university posted this picture or posted this video. Now let me explain what's going on here. This container is made out of stainless steel. In case you're thinking of trying this at home, this container is made out of stainless steel. In other words, don't try this at home. There are windows here that are made out of sapphire, which that's a pretty reasonable way to do it. The sapphire windows work pretty well. Usually you'd put all this behind a blast shield in case something ruptured. Then that way you're not gonna get shattered sapphire all over you, and also you don't want chunks of stuff flying at you in case the thing were to rupture. So you'll get a blast shield. But the sapphire makes it possible to look into the vessel. Right here we've got liquid at the bottom, and then the gas phase is above. This is just a tube that it was used to feed in the carbon dioxide into that container. So that's easy enough. All right, so now I'm going to play the video. There's not any sound to the video, so I'll describe what's going on. The temperature right now is below that 31 degrees Celsius that we saw earlier, and the pressure is also well below the 73 atmospheres. Okay, but they're slowly heating it up. You can tell because of these waves here that they're heating it up. And as they heat it up, the density of that liquid is decreasing. The density of the gas is increasing. And so the densities are getting closer and closer to each other. So the densities are getting closer and closer to each other. So as they do, you'll notice that this meniscus, the line between the liquid and the gas, start to get a little hazy, a little bit difficult to see. You can start to see it looks a little bit hazy there. All right, it's getting more difficult to see that meniscus. You can still kind of see it there, but it's getting more difficult. All right, it's getting closer. Now they're almost the same. You can still see a little bit of a meniscus right here, but we're almost to the critical point. All right, you can start to see that meniscus is almost completely gone. There's just a little bit left. All right, So at this point, we pretty much have a supercritical carbon dioxide. And that is, again, at very approachable and fairly easy to get temperature pressure combinations. So with a reasonable setup, you could do this. Now, again, don't do this at home because this is not something you want to mess around with at home. But pretty cool video. All right, so that is that. All right. Oh, and then if you get interested, check out this one from Applied Science. It's kind of fascinating. He made one at home. Again, I recommend not doing this, but this guy made one at home. I admire that he did this, but it's very dangerous. Instead of using stainless steel, he used aluminum, and instead of using sapphire windows, he just got some acrylic. I love Home Scientist. Anyway, check out that guy. That's interesting stuff. All right. Well, one of the uses for supercritical carbon dioxide is that it's a very convenient way to dissolve non-polar molecules that are a little bit basic. Turns out carbon dioxide is a little bit acidic. It's very good at dissolving bases like caffeine. And so one of the tricks that they do with supercritical carbon dioxide is that they will take coffee beans and they will extract the caffeine out of the coffee beans using the supercritical fluid. They pump that supercritical fluid with caffeine over to another container, evaporate the carbon dioxide, and they're left with almost pure caffeine. Not quite pure, but almost pure caffeine. So they add value to the coffee by making it decaffeinated, although at that point, what's the point of drinking the coffee if it doesn't have any caffeine in it? And then they can take that caffeine that they extract from the coffee and they can put it in other things like sodas and stuff. So very cool process that they do there. All right. Well, that's the end of chapter 11. Immediately after this, I'm going to do a short segment on chapter 12, which is our next page on the in-class assignment. And so I will do that here in just a second.